Welcome to this explainer. Back when the United States and the Soviet Union were locked in the space race, humanity had to build what is arguably one of the most brilliant and seriously constrained pieces of engineering in history. We're talking about the Apollo guidance computer. MIT's instrumentation lab had to figure out a way to pull off autonomous lunar navigation and landing from scratch. It is just a fascinating story of how extreme limitations practically forced engineers to invent the modern computing era.
All right, let's just dive right into this. How on earth did a computer with only 2 kilobytes, yes, 2K of erasable active memory, safely land human beings on the moon? To put that into perspective for you, a simple text email you'd send today, that takes up more memory than the active RAM used to guide a spacecraft literally 240,000 miles away. It sounds absolutely impossible, right? But it worked, and it worked flawlessly. So let's unpack exactly how MIT pulled this off.
To really grasp this monumental achievement, we have to think about the physical reality of navigating a spacecraft in a total vacuum. Out there, the lunar module was operating in an environment completely devoid of atmospheric friction. Every single tiny burst from a thruster permanently changed its trajectory. Human reflexes? Yeah, they just aren't fast enough or precise enough to calculate orbital mechanics in your head and execute a soft lunar touchdown manually. They absolutely 100% needed a computer.
And the requirements for that computer, they were just staggering. MIT engineers were tasked with designing a system that could juggle incredibly complex, real-time navigation tasks all at once. It had to autonomously navigate the massive void from Earth to the moon, constantly calculate its exact 3D position and speed, and even use the stars to verify its path. On top of all that, it acted as a digital autopilot to execute the landing, the ascent, and the rendezvous. Talk about the ultimate to-do list for a 1960s machine.
Okay, let's move into Section 1. Inside the hardware, building for space.
Now picture a computer in the 1960s. You're probably visualizing a massive machine taking up an entire room, right? So how did they fit one inside a tiny spacecraft? Well, if we peel back the chassis of the Apollo guidance computer, we see this really brilliant physical divide. There's an upper tray built specifically for memory, and a lower tray strictly dedicated to logic modules. Because traditional circuit boards back then just couldn't give them the logic density they needed for space, they connected everything using these incredibly dense wire wraps right underneath the logic tray.
If we zoom in a bit closer on that lower tray, we find what they called logic sticks. These were subassemblies, and each one contained 120 identical chips welded onto multi-layer boards. And, standardizing the hardware like this, it was an absolute stroke of genius. It simplified the whole design and made the rigorous testing they needed actually manageable.
Take a look at the scale of this. These are Fairchild micro logic chips, mounted directly onto the logic stick. They were incredibly simple, featuring just 2 basic NOR logic gates per chip. Think about that for a second. The immense, complex logic required to navigate a ship to the moon was built by flat-packing hundreds of thousands of these tiny, extremely basic 2-gate chips together.
And well, when you wire hundreds of thousands of these simple chips together, you create what the engineers affectionately and, let's be honest, highly accurately called a spaghetti diagram of logical pathways. This central processor had to talk to literally everything: the engines, the optics, radars, analog gauges, the whole shebang. Managing that chaotic web of connections with absolute pinpoint control and zero margin for error is honestly one of the greatest crowning achievements of the whole space program.
So to clear up some of that spaghetti and actually make sense of how the spacecraft was moving, the computer heavily relied on the Inertial Measurement Unit, or IMU. Think of it as a super sophisticated system of gyroscopes and accelerometers. It constantly fed the computer critical spatial and positioning data in real time, which meant the machine always knew exactly how the spacecraft was oriented out there in the void.
All right, that brings us to Section 2, software and memory, weaving the code.
To handle the software, the memory architecture was physically divided. First up, you have the core ropes, and yes, I mean that literally. Engineers physically wove the operating instructions into these ropes for read-only storage. If a wire passed through a tiny magnetic ring, it was a 1. If it bypassed it, a 0.
Once that was woven, the code was hardwired and completely crash-proof. Then, for the active, on-the-fly calculations, they relied on that shockingly small 2K of conventional read-write memory we talked about earlier. But this super tight constraint brings up a massive question. How did the system handle real-time emergencies? What happens when this tiny computer, which is designed to juggle just a few long and short tasks, suddenly gets completely overwhelmed by a flood of critical radar or engine data during a high-stakes lunar descent? Well, their solution was something called involuntary instructions. When a piece of external hardware, like that IMU we mentioned, needed to urgently update the computer, it didn't crash the whole system, and it didn't even interrupt the program that was currently running. Instead, the hardware would directly update the memory counters in the background, which delayed processing by only about 20 microseconds. It was a completely revolutionary feature, and it quite literally saved the mission from crashing when the computer was bombarded with radar data during the Apollo 11 descent.
Moving right along to Section 3, the human interface, talking to the machine.
So you might be wondering, how exactly do astronauts communicate with a complex operating system while wearing those massive, bulky space gloves? The answer is the DSK. That stands for Display and Keyboard. It gave them a really elegant, robust interface using a super simple noun/verb syntax. Basically, you input an action, which is the verb, and an object to perform that action on, which is the noun. It's so intuitive, it's pretty much the granddaddy of the modern command line interface. For example, if you punch in verb 06, noun 33, you are commanding the computer to instantly give you a mission-critical variable. Verb 06 means display values, and noun 33 means time of ignition. So the D-Sky would light up with the precise mission time, say 10:40 hours, 30 minutes, and 10.94 seconds. It told the crew exactly, down to the centisecond, when those engines needed to fire. No guesswork involved. And that leads us to our final part, Section 4, capturing the final result, the scientific payoff. Getting the spacecraft safely down to the lunar surface wasn't just a stunt to beat the Soviets, right? It was the gateway to conducting real, groundbreaking science. Because the Apollo guidance computer took on the immense, heavy lifting of navigating the lunar module to the surface, the astronauts could safely transition from survival mode into being actual surface explorers, all while the command and service module stayed perfectly safe in orbit.
And once they were actually on the surface, the astronauts deployed scientific tools that were a massive contrast to the crazy complexity of the guidance computer. Take the Apollo lunar surface close-up camera, for instance. Built by Kodak, it was optimized for total operational simplicity. It was an automatic, self-powered, twin-lens stereoscopic camera with fixed focus and fixed flash. You just set it down and shoot. The computer did all the brutal math so the crew could easily use tools like this to capture things like lunar dust details down to 80 micrometers on color film.
It's just incredible. To overcome the extreme limitations of space, weight, and power back in the 1960s, MIT engineers didn't just get humanity to the moon. They literally birthed the foundations of the real-time operating systems and digital fly-by-wire technologies that run our modern world today. So it really makes you wonder, what extreme constraints in our world right now are quietly forcing the next massive leap in human innovation?